What if I told you there's a way to solve a classic coding challenge, not just correctly, but in the most efficient way possible, with a single, elegant pass through the data? Well, get ready because today we're unlocking a powerful technique called the monotonic stack.
So, let's set the stage. Here's the core problem, a real favorite in coding interviews, often called next greater element. Imagine you have a list of numbers. For every single one of them, your job is to look to the right and tell me, what's the very first number you see that's bigger? How would you even start to tackle that?
Now, your first instinct, and that's totally normal, is probably to just use brute force. You take the first number, then start a second loop to check everything to its right? And yeah, that'll give you the correct answer. But in a technical interview, that's a trap. It's just way too slow.
And this right here shows you exactly why. The nested loop approach, that's O of n squared, which means as your list gets bigger, the time it takes just explodes. You're going to get a timeout error. The monotonic stack, though, that's O of n, or linear time. It's a straight shot. This is literally the difference between a failed test case and an accepted solution. Okay, so let's get on the same page and formally define what we're up against. This is the next greater challenge. So what does that actually mean? It means two things are absolutely critical. One, the bigger number has to be to the right, so its index j has to be greater than our current index I. And two, it has to be the first one you run into, not just any bigger number, the next one. And if you get to the end of the list and find nothing, its next greater element is just null or empty.
Now for the fun part. The absolute best way to wrap your head around the monotonic stack is with a really simple, powerful analogy. Let's think of it as the decreasing staircase trick.
Picture this in your mind. You've got a stack, but it's a special stack. It's like a line of people standing on each other's shoulders, but with one very strict rule. The person at the bottom is the tallest, the one above them is a little shorter, and the person at the very top is the shortest of all. We always have to keep this decreasing order.
So here's how the game is played. A new person or a new number shows up. We look at the person at the very top of our staircase. Is the new person taller? If they are, bam! We've just found the next greater element for the person on top. So that person on top gets to leave and we record their answer. We keep doing this, checking the new person against the new top of the stack until our staircase rule is true again. Once it is, the new person can finally join the stack.
Okay, I know that might sound a little abstract, so let's make it super concrete. We're going to walk through a simple example and see this staircase in action.
All right, our array is 2, 1, 4. Simple enough. First up is the number 2, which is at index 0. Our stack is totally empty, so there's nothing to compare it to. We just add its index, which is 0, to the stack. Easy.
Next, the number 1 arrives. So we ask the question, is 1 greater than the number at the top of our stack? The top of our stack is index 0, which corresponds to the number 2. Is 1 bigger than 2? Nope. So our decreasing staircase rule is perfectly fine. We just add the index for 1, which is 1, right on top.
And now, this is where the magic happens. The number 4 arrives. We look at the top of the stack, which is index 1, the number 1. Is 4 bigger than 1? Oh, yes it is. So we know that 4 is the next greater element for 1. We pop 1's index off the stack and we fill in our result. But we're not done. We look at the new top of the stack, index 0, which is the number 2. Is 4 bigger than 2? Yes again. So 4 is also the next greater element for 2. We pop 2's index, fill in the result. Now the stack is empty, and 4 can finally be added.
Okay, so we've got the intuition, we've seen the logic play out. Now let's see how that whole staircase idea translates directly into some clean Python code.
And here it is. You'll be surprised how simple it is. We start with an empty stack for our indices and a result array to store the answers. Then we just loop through our input array. And this while loop, this is the heart of it all. It checks two things. First, is there anything even in the stack? And second, is our current number bigger than the number at the top of the stack? If both are true, we pop the index from the stack because we've found its next greater element. It's our current number. Once that loop is finished, we add our current index to the stack and move on. That's the whole thing.
Seriously, this one while loop, that is the staircase rule. It's like the bouncer at the door of a club, making sure that only a strictly decreasing line of people can stay inside the stack. This little loop does all the heavy lifting of finding and processing all those next greater elements. So why on earth do we go through all this trouble with stacks and staircase analogies? Well, the payoff is huge, and it all comes down to one thing:
Speed. Just think about it for a second. Over the entire course of the algorithm, every single number's index gets pushed onto the stack one time. Exactly once. And it gets popped at most one time. Since every element is only touched a constant number of times, the total time to run the algorithm is directly proportional to the size of the array. And that gives us that beautiful, efficient, ON linear time. This visual really says it all. The time for that naive ON squared solution just skyrockets as the input grows. It gets slow, really, really fast. But our monotonic stack solution? It's that gentle, predictable, straight line. For any real-world input size, this isn't just a small improvement. It's the difference between a solution that actually works and one that just doesn't.
And here's why this matters so much. This isn't just a one-off trick for a single problem. The monotonic stack is a fundamental pattern. It is the key that unlocks a whole family of tricky, popular interview questions. Once you really understand this pattern, you'll start seeing it pop up everywhere.
And hey, quick pro tip for you. What if the array was circular? You know, where you can wrap around from the end back to the beginning? It's actually a simple fix. You just run the same algorithm on the array twice, as if it were concatenated with itself. That's a 2n operation, which, in the world of big O, is still just O of n. The beautiful efficiency holds up.
So the big takeaway is this. By maintaining one simple, ordered stack, you can solve these tricky, neighbor-finding problems with incredible efficiency. We've totally mastered finding the next greater element to the right. But now, a challenge for you. How would you tweak this logic to find the previous, smaller element to the left? Think about it. All the tools you need are right there.